Welcome to lecture 6 of the wireless communication course. Today we will learn about something called diversity, which is a useful tool to combat the poor error performance under fading. So let's suppose, just to give you an example and maybe help you remember diversity, let's suppose that you want to send a rocket from Earth to the moon. This is the moon. This is your rocket. You want to go here, and you have to put some computers in this rocket. And let's suppose that during the mission, this round-trip mission, each of the computers has a probability of 0.01 to fail. Right. You put your computer in this rocket, or you put it here. Would this be an acceptable probability to fail? So that means 1 in 100 missions will fail because the rocket would explode. And what would you do to mitigate this risk? And the way that you mitigate this risk is by putting, instead of one computer, you put n computers. And they are operating independently. So maybe you want to have them made by different vendors with independently written software, with independent power sources. And under those assumptions, then the probability to fail will be p to the power n, right? So you can put n equal to 2, then you put 0.01 times 0.01, which is already much smaller, and so forth. And this is really the idea of diversity, is that you will create multiple signal paths which experience independent fading, and then by creating this multiple independent signal paths, you hope that at least one of the paths will work out and will allow you to send your data. And this is also shown in this picture, which shows, I guess, 3 communication channels over time, and while each of them varies a lot, if you look at the maximum of all of the 3, this is actually relatively stable. And again, these are just examples of what is diversity. So with this toy example behind us, let's move on to today's topics. What we will cover today will be, you can find in chapter 7 of the book, and there's some recommended sections for you here. Today's learning outcomes, we will learn about diversity in space, time, and frequency. We will talk about how to do combining for diversity, linear combining, maximum ratio combining, selection combining. You should be able to draw block diagrams of combining schemes, determine output SNR, and then evaluate outage and average error probability after combining. You should also be able to explain the difference between array gain and diversity gain. So we will cover all of these today. Before we do that, a brief recap of last time. We saw last time that there are different notions of received power after path loss only, given by this path loss equation. Received power due to path loss and shadowing, which is here the received power due to path loss only with a Gaussian perturbation. So I can write this as the received power after path loss in dB domain plus a Gaussian variable. The received power after multipath is written as PR without any bars. This is given by the received power after path loss and shadowing multiplied with an exponential random variable. Maybe I didn't explain this very properly, but this just means that I multiply it with a random variable r, which is drawn from an exponential distribution with parameter 1. Okay, and then PR is equal to r times PR bar. So that means that the mean of r will be given by PR bar. Given these definitions of the received power, we also have different definition of the signal-to-noise ratio. Without bar is after path loss, shadowing, and multipath. With 1 bar is path loss and shadowing, and 2 bars is with path loss only. This then gives rise to different SNR distributions. This is the SNR distribution after path loss, shadowing, and multipath fading, with an average value that depends on path loss and shadowing SNR. We also have the distribution of the SNR after path loss and shadowing, which has a Gaussian distribution in the dB domain, where the average value depends on the path loss only SNR. We've also seen that under Rayleigh fading, under the narrowband model, the channel changes over time, which is shown here in blue. Sometimes it's good, sometimes it's bad. And to compute the performance of communication over such channels, we have two different metrics. Outage probability, the probability that the SNR is below some threshold value, and this threshold value can be related, for instance, to a symbol error rate, or the average error probability, which is given by the integral or the expected value of the error probability over all possible SNRs. And these are used under different conditions. We've seen that when we evaluated this average error probability and compared really fading with the additive white Gaussian noise channel, there's an enormous gap, which means that to have the same performance, we need to use much more transmit power under Rayleigh fading. And today, what we will really try to do is try to close this gap. So to have operation going from the Rayleigh all the way back to the additive white Gaussian noise channel, which will come, of course, at a price. And the way that we get there is through diversity. Last time we've also talked about differential phase shift keying, which is a non-coherent way of communication in which we send information on phase differences rather than absolute phase. And we saw that even when the SNR goes to infinity, there is something called an error floor. That means no matter how high your SNR is, just because the channel is changing slightly from one transmission to the next, your symbol error rate will be limited to this value. And the error floor depends on how quickly the channel is changing, which in turn depends on the Doppler that you're experiencing. Good, then now we can move on to our topic of today, which is diversity. The idea of diversity is to send the same signal over multiple independent channels. Now, typically when you're sending the signal, the path loss and shadowing will be the same every time you send it if you don't move a lot. But definitely the fast fading and the noise will be different. So this is what creates independence. And then you have multiple outputs, one for each of these so-called diversity branches. So here we have signal paths or diversity branches. And again, the idea is that even though maybe one of the channels will be bad, one of the branches will be bad, hopefully the other one will be good and you are able to recover your data. So now the question is, how do we generate such independent paths? There are different ways to do this. You can do diversity in space using multiple antennas, diversity in time by sending the same signal multiple times, or diversity in frequency by sending the same signal over different frequency bands. And now a question for you is, how far apart would you put your antennas? How far apart would you put your transmissions? And how far apart would you put your communication bands to have independent signals? I should also point out that it's not strictly needed to have independent signals. You could have correlated channels, but then the performance, of course, will suffer. So as before, I recommend you pause the video and then come back when you've solved this problem. Good, so we've discussed three different ways of creating diversity: time, frequency, and space. So when we have time diversity, what we do is we send the same symbol multiple times, let's say m times, but we should wait at least one coherence time in between. So let's say that we send symbol 1 here, and then we send it again here. So we send this exactly the same data, but the time in between should be larger than the coherence time, so that the channel, the first time it is sent, so we'll have a certain channel H1 and this channel H1 tilde, that these are independent. And then we could send it another time here, H1 tilde tilde. So that's the channel seen by this first packet over different times. And these are all independent. Good, and of course on the x-axis here is time. In frequency diversity, we have on the x-axis frequency, so that we have a certain communication band that we are using. We divide this up into many smaller bands. This could be done with different techniques, for instance OFDM, and we send over different subcarriers or over these smaller bands the same data multiple times, but we space them apart more than the coherence bandwidth. And this again creates independent channels for each of these red blocks, independent channels for each of these blue and green and yellow blocks as well. A third way is to use space diversity, in which we send the symbol only one time, or we send our data only one time, but we use M antennas. These antennas could be at the receiver, at the transmitter. Let's say they're at the receiver. So in this case, we will have a model that looks something like this. We have a transmitter sending a symbol, let's say S. We have a receiver with 3 antennas here. For each of the antennas, we have a channel, H1, H2, H3, and then receive on the first antenna, Y1 is H1S plus N1, Y2 is H2S plus N2, and Y3 is H3S plus N3. Now, for these channels to be independent, we need that the spacing between the antennas is more than lambda over 2. This lambda over 2, where does this come from? This comes from lecture 3, from the Jakes model, right? Which tells you that the autocorrelation function of the channel is approximately 0 when we have a displacement delta t times v of approximately 0.4 lambda. So this tells us that if the antennas are placed about half a wavelength apart, the correlation between them will be 0, so we have independent channels if the channel is Gaussian. This is only true under a rich scattering or really fading environment. So now we've created this diversity branches. The question is now, what should I do? What processing do I need to do to have a decision on S, to be able to recover my S? And this is what this next slide is about. And while we haven't seen how to do processing for diversity, actually you have all the tools necessary to solve this problem. So suppose that you have a discrete time communication system with m independent fading channels. Okay, and this could be in time, frequency, or space, it doesn't really matter, with equal statistics. So the distribution of each of the channels is the same. We send a common input symbol S, and we have outputs y1 through ym. So just as before, and we write these outputs as follows. yi is the channel, which is given by an amplitude and a phase, times the data plus noise. Okay, and this S is unknown. The noise is just standard complex Gaussian, IID, and we assume that these channels are known. So we've sent some training sequence or a pilot, and we've estimated these channels. Now I would like you to pause the video and answer these following questions. What is the instantaneous SNR per channel? What is the average SNR per channel? How would you process the vector of observations to form a maximum likelihood estimate of S? In this processing, what will be the instantaneous SNR and the average SNR? So please pause the video and then come back once you've solved this problem. So I have the solution on the next slide, but let's see if I can derive this in real time. Or at least part of the solution. Good, so we have observations yi, which are equal to, let's say, beta I s plus ni. Here beta I is ai e to the power j theta I from 1 to m. Now the instantaneous SNR on channel I is given by the signal power, so this would be ai squared times the signal energy over the noise power. So this is the instantaneous SNR on channel I. The average SNR on channel I will be the expectation of ai squared times the energy of S squared over N naught. Okay, good. So that's the first part. Now, how to do the combining? We follow the maximum likelihood principle. So we first aggregate all the observations in a vector y, which is y1 till ym. And then we compute p of y given S. Okay, I should also condition the beta i's, but they are given, so I will not worry about that. Okay, and this will be some constant, which I don't care about, exponential minus 1 over n naught. And now I'm not sure if it's n naught over 2 or n naught. I think n naught over 2. And then sum I from 1 to m yi minus beta I s squared. Okay, and here I've used the fact that we have independent transmissions. Right, so this is also equal to product I from 1 to m p of yi given s, which is product I from 1 to m, some constant ci exponential minus 2 over n naught yi minus beta I s squared, and then I can bring this product inside of here, and this leads to a sum. Okay, and then I know that s hat for our specific vector y is equal to arg max over all possible s's. So I find the s that maximizes p of y given s. I know that I can also write this as args max over s log p of y given s, because the logarithm is a monotonically increasing function. I can then plug whatever this function in here. So this is arg max over s minus 2 over n naught sum I from 1 to m yi minus beta I s squared. Good, then this is just a constant, and then this I can replace by using minimum instead of maximum. And I can write this also compact as arg min over s. Now the vector norm y minus beta s squared. Okay, so here I've used vector norm, which is defined as follows. For a vector x, this squared is just sum over all of the entries xi squared. That's the definition. Okay, so I will do a minimum Euclidean distance based on this observation. Now it turns out I can actually go one step further, sorry. I can write this squared norm out. So this is norm of y squared plus norm of beta squared s squared minus 2 times the real part of, let's see, beta Hermitian ys. Good. So I've just written out this squared norm, and what you notice is that in this squared norm, well, this does not matter, right, because it doesn't depend on s. And then in what remains, the only thing that depends on the observation is this. So I can create a kind of compressed observation. Which I call z, which is equal to beta Hermitian y. Okay, and this is just a complex number, while beta and y are vectors. For those of you who haven't seen this Hermitian symbol, let me just define this. I'm running a bit low on space. So beta Hermitian is equal to beta transposed, which turns a column vector to a row vector and vice versa, and then complex conjugate. So that's the definition. Good. Since I'm out of space, I will move on to the solution that I've written down here. Good. So instantaneous SNR per channel is the expression that we found. So this is the energy of the symbols, the channel gain squared over the noise. Average SNR, so I average over both the signal and the channel, and they're independent, so I can write this expectation out like this. Maximum likelihood detector is I maximize the likelihood function. Now I can take the logarithm of this, and this log likelihood function is given by this squared norm with a minus sign, where beta contains all the complex channel coefficients. I can write this out. In the end, I get this expression with the square root of the observation, the square root of the channel and the signal, and then this product of the observation with this beta Hermitian. And this beta Hermitian is called a sufficient statistic. So this means that if I tell you beta Hermitian, right, and I call this, as I said before, I call this z, right, it's just a number, and I replace this here by z, and you don't know why, you don't know beta, then you can still solve this maximum likelihood problem. Well, you need to know beta, but you don't need to know the observation y. So it's a compressed observation that tells you everything you need to know to make a decision. So knowing this observation z is sufficient to make a maximum likelihood decision. Right, so now this z here, this complex number, I can expand this because I know that y is beta times s plus noise. Okay, so then this z is equal to the norm of beta squared times s plus beta Hermitian times the noise. And now again, I can compute the SNR. So I can compute the power of this squared divided by the power of this one squared. So that's this first expression. This is the instantaneous SNR. I can then expand this thing here, which will give me this expression. And I will actually try to do that. Now I have beta Hermitian squared and beta Hermitian here like this. So this cancels out. I can write out what beta Hermitian beta is. So this is the sum of the squares of the amplitudes. And now if I look closely, I find that this is exactly the sum of the individual SNRs. Okay, so this is important. Output SNR is sum of the input SNRs. Now the only thing that maybe we can spend a few more minutes on is how to compute this. So let's see where I can do this. Zoom in. Expectation of beta Hermitian n. Oh, let's see the expression. Squared, okay. Okay, beta and n are vectors. So now I will make use of the fact that absolute value of x squared is x times x complex conjugate. So this is expectation of beta Hermitian n and Hermitian beta, right? Now I will make use that beta is, in this case, beta is fixed because it's the instantaneous SNR. So then this becomes beta Hermitian expectation and Hermitian beta. So the expectation is only over n. Now I will make use of the fact that the noise is white. Right, so the different, or I would say independent across the branches. IID. So this means that I have beta Hermitian n naught times an identity matrix of m by m times beta. So I find n naught beta Hermitian beta. Okay, and I will do my best to write these bars to show that they are vectors, but I'm not very careful in that. And hopefully this is the correct results. Yes, it is. Good. So this, let's take a break now. Thank you.